Okay, in the last class, we were talking about the paged memory management, and we have seen that in case of paged memory management, the logical address space of a job is divided into a number of pages where every page is of equal size, and the main memory is also divided into a number of partitions of the same size, where the partitions in the main memory are called frames. Okay. And we can put any page in any of the frames, and because of this, it is not necessary that if you have a job of say 40 kilobytes, you have to have 40 kilobytes memory contiguously available for loading that job. So even if we have pages of 10 kilobytes each, in that case, if I have say 4 frames available in the main memory, even if the frames are not available in contiguous memory locations, I can still load the job into the main memory, which will be loaded into 4 different frames, and the job can be executed. So in that case, whenever the CPU generates an address, the address is to be converted into a 2-component address. One component will be the page number, and the other component is the offset within the page. So it is in the form of a doublet consisting of page number and offset within the page. So what we have seen is, using the page number for memory access, using the page number, you have to go to the page map table. The corresponding entry in the page map table will tell you the frame number where that page is loaded. So once you have the frame number, then from the frame number, then size of the page and offset within the page, you can find out that what is the physical address of the memory that is to be accessed. Now, when we go for this paged memory management technique, then we get another advantage, that is sharing of code. So same code may be shared by more than one user program. Say for example, there are 2 users who are trying to edit their files. Okay. So there is a single program which is the edit program. Okay. And for 2 users, there may be 2 data files which are to be edited. So for user 1, there will be data file 1, data 1. For user 2, there will be data 2. Okay. Whereas the edit code is same, the program edit is same. So if I see the logical address space of these 2 users, the logical address space of user 1 will appear something like this. Firstly, it will have the code corresponding to the program edit, and then the data part or data 1. Similarly, for user 2, it will be the same code edit, but in this case, the data part will be data 2. Okay. Usually what we have is, whenever 2 instances of the same program, that is edit, is executed, we will have 2 copies of the same program in the main memory. One copy for user 1, the other copy for user 2. Okay, that means we have to have duplicate copies of the same user program which are being used by 2 different users. But when we go for this paged memory management technique, it is possible that the same code can be shared by both the users, but the data part will be different. Okay. So if I break this logical address space of user 1 into a number of pages, it can appear something like this. So I'll have a number of pages for edit. So for edit, I can put it like this. Say page number 0, E0, then E1 and E2. Suppose the edit code, the logical space for edit code is divided into 3 such pages, E0, E1 and E2. For data part, it will be a different page. So if this data is contained in a single page, in that case, this will be say D0 for user 1. So I'll put it as D01. Similarly, for user 2, the logical address space can be broken in similar way. The edit code will remain the same. So it will be same E0, E1 and E2. These are the pages corresponding to the edit code. The data part, if it is broken into two different pages, it will be D02, okay, for user 2, data page number 0 and D12. Okay. So this is the logical address space of user 1 and this is the logical address space of user 2. Now coming to the main memory, the frames in the main memory can be something like this. As before, initial one or more frames will be allocated to the operating system. The remaining number of frames which are available to the user can be used for placing the pages corresponding to the edit code and also for placing the pages corresponding to the data of different users. Okay. So if the situation is something like this, so this frame contains page number 0 of the edit code, this frame may contain page number 1 of the edit code, this frame may contain page number 2 of the edit code. This frame may contain D01, this frame may contain D02 and this frame may contain D12, something like this. Now if you look at the frame number, so this is frame number 0, this is frame number 1, this is frame number 2, this is frame number 3, 4, 5, 6, 7, 8, 9, 10 and 11. Okay. So to enable sharing of the same code by both the users, what you have to do is we have to simply generate the page map table accordingly. Okay. So in this case, for page map table of user program 1, I call it PMT1, will be something like this. This is page map table 1 for user program 1. So for filling up this page map table of user program 1, what I have to say is what is the logical address space of user program 1. So 0th page of user 1's logical address space is E0. Okay. So the first entry in this page map table 1 will be the frame number where E0 is loaded. So here frame number is 1. So the first entry in this page map table 1 will contain value 1. The second entry will contain the frame number where E1 is loaded. So in this case, E1 is loaded in frame number 3. So the second entry will contain frame number 3. Similarly, the third entry will contain the frame number where E2 is loaded. E2 is loaded in frame number 7. So this entry will be frame number 7. Okay. Next entry will be the frame number where D01 is loaded. So D01 is loaded in frame number 2. So here the entry will be frame number 2. Similarly, I can also construct the page map table for user program 2. So this is PMT2. And here, because the first three pages are shared, okay, so content of the first 3 entries in PMT2 will be same as the first 3 entries in PMT1. So this will contain 1, 3 and 7. Next 2 entries will correspond to the data pages of user program 2. So here D02 is loaded in frame number 9. So this entry will be 9. D12 is loaded in frame number 11. So this entry will be 11. Okay. So if I have these types of page map table for 2 user programs, user program 1 and user program 2, you find that first 3 pages are actually shared by user program 1 and user program 2. Now what restriction we have to have if we want to allow such sharing of code? the code should be reentrant. That means it should not be self-modifying. If I have a program which while execution modifies itself, then that cannot be shared, because maybe the modification is required for user program 1, but the modification is not expected, not desired for user program 2. In that case, such sharing is not possible. But if the code is not self-modifying, in that case we can share the codes among a number of users, not only 2, even 3, 4 users can share the same copy of the code which is there in the main memory. Okay. Now, when you construct such a page map table, you find that the protection that we have said in case of other memory management techniques like MFT or MVT, that we want that one user program should not try to access or modify the address space of some other user program. Similar such protection should also be available in case of paged memory management technique. So you find that 2 of the entries I have kept intentionally blank. The reason being, whenever I create a page map table, I have to decide what will be the maximum size of the page map table. That means, what is the size of the jobs that are going to be executed on the system? Okay. And if I know what is the maximum size and I know what is the page size, from that I can find out what is the maximum number of pages of the logical address space of a job that will be executed on the system. So accordingly, I set the page map table. That means how many entries this page map table will have. Now, out of these entries, all the entries are not going to be filled up, because the number of pages of a particular job may be less than the maximum number of entries. So in that case, some of the entries will be left blank. Right? So whenever I set this page map table, I have to identify that which entries in this page map table are valid and which entries in this page map table are invalid. Okay. So there is an additional bit which is called a valid invalid bit. Either it is valid or invalid. So for every entry, there is an additional bit. Okay. So the entries in this page map table which contain the valid page numbers, the corresponding entries, the corresponding valid invalid bit may be set to 1. Other entries will be set to 0. Okay. So similarly here, the valid invalid bit all these bits are set to 1, or it may be the reverse, but what you do that you should take care in the programming. Okay. So assume that any entry in the page map table which contains a valid frame number or entry corresponding to a valid page number, the corresponding valid and invalid bit should be set to 1. The entries which are not valid, the valid invalid bit in those entries should contain a value 0. Okay. So once I have this valid invalid bit, even if an user program generates an address which gives a page number which does not belong to the logical address space of that particular program, in that case I will come to an entry in this page map table where the valid invalid bit is 0. Okay. So before extracting the frame number, you have to check what is the valid invalid bit content. If the valid invalid bit is equal to 1, I know that the page that is being accessed is a valid page. So you extract the corresponding frame number, then from the frame number and the offset within the page, you go to the corresponding physical address in the main memory and access the corresponding location. In case a page number is generated which does not belong to the logical address space of that user program, then you come to an entry for which the valid invalid bit content is 0. So the moment it is 0, you know that the user program is trying to access some page or some frame in the main memory which actually does not belong to that user program. So immediately there has to be an interrupt, following which the program will be terminated. Okay. So even in this paged memory management, I can have the protection mechanism through this valid invalid bit. Okay. And I can also go for sharing of the codes by properly setting the values in the page map tables. But as we said in the last class, that in case of paged memory management, where every page is of same size or every frame is of same size, this does not take care of the modular structure of the program. Okay. So that modular structure can be taken care of by another memory management technique which is similar to this, is called a segmented memory management technique. Now, what is this segmented memory management? We have said that whenever you write a program, you usually organize the program in a number of functions, and the functions are to be called. Now, whatever I am saying, that is with respect to procedural language, not with respect to object-oriented language. Okay, because in case of object-oriented language, it is very difficult to get some functions like that, though it is not impossible. But in procedural language programs, such functions or structures are quite evident. So whenever we write a program using some procedural language, what we do is, normally we organize the program into a number of functions, and you call those functions from the main program. Okay. So there is always a function which is called a main function. Okay. And there may be many other functions which are actually called by the main function in some order. Okay. So other functions may be, say, square root, maybe another one function. Factorial, maybe another function. So there may be various such functions like this. Say, I can have a function called billing. Maybe I write a program for pay bill section. So there may be a function called billing, and many other functions like this. Okay. Now all these functions taken together, they form the logical address space of the entire program. Okay. And it is quite obvious that these different functions may not be of same size. In general, different functions will be of different size. Okay. So in the memory management technique, if I want to maintain the logical structure of the program or the modular structure of the program, then instead of having pages of same size, instead of breaking the logical address space of the user program into pages of same size, it is quite logical that you break the logical address space of the program into a number of partitions or number of segments, where every segment will correspond to one such function. So the idea is, whenever I load a program, it is quite natural that different functions of the program should be available in a block of memory. Okay. So the main function will be available in one block of memory. Square root, sqrt will be available in another block of memory. Factorial will be available in another block of memory. Billing will be available in another block of memory, and so on. So effectively what we are doing is, we are breaking this logical address space into a number of segments. So unlike in the previous case, where we call them as pages, where pages are of same size, in case of this segmented memory management, we break the program into a number of segments, where the segments can be of different size. Okay. Now following this, the kind of memory partitioning that will be more suitable for segmented memory management is not breaking the main memory into a number of frames of same size, but the memory partitioning should be something like what we have done in case of MVT technique. That is, you create a partition whenever it is needed and of the required size. Right? So whenever I load a function, say main, in the main memory, the main function will be loaded starting from some certain location. Okay. So that location, so suppose in the main memory, I load the main function. So this is our main memory. I load the main function somewhere here. Okay. So the starting location of this partition where the main function is loaded, I call it the base address of the segment main. Okay. And the length of the segment is the limit. The concept which we have also used in case of other memory management techniques. Okay. So I have, so this is where the program main is loaded, the function main is loaded. So for function main or segment main, I'll have a base address. Segment main will have certain length, so there will be a limit of this segment. Okay. And now, whenever the CPU generates an address, in the earlier case, the address was of two components, the page number and offset within the page. Now again the address will be of two components, but instead of page number, it will be segment number. Segment number S and offset within the segment the same D. And this is the logical address generated by the CPU. Which will consist of two components S and D. Okay. Now again, to map these two component address S and D to a particular physical address in the main memory, again I have to have some mapping. In case of paged memory management, the mapping was done through page map table. In case of segmented memory management, it will also be done by a similar such table, but in this case, because it is segments, these are segments, we call them as segment table. Okay. So it is the segment table which maps this two component address SD into a physical address, and this physical address points to a particular location in the main memory where the data or the instruction is to be accessed. Okay. So the entire scheme for this segmented memory management will appear like this. The CPU generates an address. The address is a two component address S and D, where S is the segment number and D is the offset within the segment. And as I said that for every segment, I will have a base address and a limit when the segment is loaded in the main memory. And it is quite obvious that the offset within the segment cannot exceed the limit. Because if the offset within the segment as generated by the CPU that exceeds the maximum limit, then obviously this function is trying to access some segment which does not belong to this function. Okay. So the first check that you have to make is whether this offset within the segment D is less than limit or not. Only when it is less than limit, then only the addressing is a valid addressing. If it becomes greater than limit, then the address is invalid. Okay. So accordingly, the segment table that we have, the segment table will have two entries. Every entry in the segment table will have two fields. One of the field is the base address, and the second field is the limit value. Okay. So whenever CPU generates this two component address S and D, using this S, you go to an entry in the segment table. Okay. So the segment table gives both the base address and the limit of the segment. First operation that I have to do is I have to check whether this offset that is generated is less than or limit or not. Okay. So again, I will compare this D with limit. Right. So my condition is that D should be less than limit. If D is less than limit, That means if this condition is true, then what I have to do? I have to add base address to this offset. Okay. So the content of the base address will be added to offset D. That gives you the physical address in the main memory where the data or the instruction is to be accessed. So this is the main memory. Okay. And obviously, if D is not less than limit, then there has to be an interrupt following which the program is to be terminated. Okay. So this is the overall scheme of the segmented memory management. Okay. So here you find that unlike in case of paged memory management, where given the logical address space of any job, the page numbers becomes unique, provided your page size is fixed. But in this case, what I have to do is, for every segment in the logical address space, I have to give a unique segment number. Okay, and sometimes this segment number will depend upon the order in which the different functions are actually present in your user address space. Okay, so every time you recompile your program, maybe the segment number will be different. Okay, not only that, the sharing that we have said in case of paged memory management, which is very easy, the sharing of segments, because here also the sharing may be applicable. Okay, because coming back to the same example of editing some files, two or more users may like to execute the same edit program simultaneously. In that case, within the address space, the function edit becomes a common function. So if we can share that common function or the segment in which the edit code will be loaded, that code among different users, then lot of memory space can be saved. But for that, what is needed is, for every user program who are trying to share the same code, the segment number of the edit code must be same. Otherwise, you cannot share it. Okay, so that is difficult to maintain, but still that can be done, because some of the application programs, because edit is nothing but an application program which is given by the manufacturer. So what can be done is, for some of the segments which are there as application program, you can reserve some segment numbers permanently for them. So those segments will have some permanent segment number. All other segments which are generated by the user program, that can have segment numbers beyond that. So various such methods can be adopted, and using those methods, even the segments can be shared by different users. Okay. But other problem in case of segmented memory management is breaking the main memory into a number of partitions of various sizes and maintaining information of those different partitions in the main memory, which is easy in case of paged memory management technique, because all the partitions are of same size. But here the partitions will be of different size. Okay. So similar such problems can also arise in case of segmented memory management technique. So the memory management techniques which are usually implemented is, which is a combination of both segmentation and paging technique. Okay. That is, you exploit the advantage of segmented memory management technique. Okay. And you exploit also the advantage of paged memory management technique. So in that case, for paged memory management technique, what we have done is, every user program is broken into a number of pages of same size. Okay. Now, if we replace every user program by every segment, okay, so now every segment will be divided into a number of pages of same size. So the paging technique which we applied on user programs with paged memory management technique, pure paged memory management technique, the same technique can be applied on different segments of an user program. So the first additions that we'll have is segments, then the segments will be broken into number of pages. Okay. So the kind of memory management technique which we can have is paged segmented memory management. Okay. So in case of paged memory management, we have seen that for every user program, I have to have a page map table, right? In case of paged segmented memory management, for every segment, I have to have a page map table, right? So in this case, the scheme will be something like this. The CPU generates address. Again, this address is a two-component address, but my first partitioning is segmentation. That means the entire logical address space of the user program is divided into number of segments. So this CPU will give you address, which is again a two-component address, and that is segment number and offset within the segment. Right? Now, the maximum offset is the length of the segment, the maximum offset that can be generated. Now, using this segment number, what I'll do is, again, I'll go to a segment table. The segment table, as before, will contain two entries. So, using the segment number, I go to an entry in the segment table. Okay. In the earlier case, what we have seen, that segment table contains two entries. One is the limit of the segment, that is the length of the segment, and the base address where the segment is loaded. Now, in this case, every segment is divided into number of pages. That means before I go to the physical address, I also have to know that what is the page within that segment that is being accessed. Okay. So here again, the segment table, every entry in the segment table will contain two fields. One field will give you the length of the segment that is specified as limit. Okay. And the second field, in this case, instead of giving the base address of the segment in the main memory, it will give you the base address of the page map table for this segment. Okay. So this will give you page map table base address. Okay. So here the first operation that you have to do is you have to compare this limit with D, because the same restriction is applicable that D cannot exceed limit. So I have to compare D with limit. So I have to check whether D is less than limit or not. If D is not less than limit, then there has to be a trap following which the program will be terminated. If this condition is satisfied that D is less than limit, then as I said, the segment will be, every segment will be broken into number of pages. How do you break it into number of pages? I can assume that this D that is specified by this address, this is nothing but logical address within the segment. And we are breaking every segment into number of pages. So the page number and the offset within the page that we generated from the logical address in case of paged memory management, the same can be applied on this offset D within the segment, because now every segment is replacing the every user program of paged memory management. Okay. So if this condition is satisfied, in that case D has to be broken into two components. One is the page number of the segment. So this is D. It is broken into two components, which is page number within the segment and the offset within the corresponding page. Let me put it as D prime. Okay. So once I have this page number, then using the page number, I will go to the page map table of this particular segment. Base address of the page map table is given in this entry. Okay. So what I have to do is I have to add this page number with the base address of the page map table, right? So this gives you an entry in the corresponding page map table. This is the PMT page map table of segment S, right? This one. So I know the base address. So base address corresponds to the starting location of the page map table and the particular page within this page map table that I have to look for. So I add P with the page map table base address. This gives me a particular entry within the page map table. Now this entry will contain the frame number where the page is loaded. Okay. So now what I have is I have the frame number F, and here I have the offset within the page, that is D dash. Okay. Now from F and D dash I can generate the physical address of the main memory. So this F and D dash, it will give you the physical address of the main memory, the location that has to be accessed. So this is the main memory. Is it okay? So here effectively what we have done is every segment is divided into number of pages, where all pages as before are of equal size, right? And then whatever we have applied on every user program in case of paged memory management, the same we are applying on every segment in the user program. So effectively what we are doing is we are employing or we are exploiting the advantage of segmentation. We are also exploiting the advantage of paging, because when it comes to main memory, the main memory is only divided into number of frames, where all frames are of same size. Okay. So as long as memory management, the main memory management is concerned, I am concerned about only those partitions, the partitions which are of same size. Okay. But here, to exploit the advantage of segmentation, what we have to know is, if a particular segment is divided into say 5 pages, I have to have 5 frames available in the main memory. The frames need not be contiguous. Okay. Whereas in case of segmented memory management, if a segment consists of say 40 kilobytes of memory, needs 40 kilobytes of memory, I must have a partition of size 40 kilobytes which is free. But if the page size is say 10 kilobytes, then this 40 kilobyte segment will be divided into 4 pages. Okay. So now when I exploited the advantage of paged memory management over this segmentation, now what I need is I need 4 different frames to be available in the main memory. The frames need not be contiguous. They may be scattered anywhere within the main memory. But I need 4 different frames, 4 free frames, where I can load this entire segment. And that mapping will be given by this page map table of that particular segment. Okay. The initial mapping on the segmentation is given by the segment table. Right. So following this, I can exploit the advantage of both the segmentation and paging. And this particular aspect will be more clear when you go for virtual memory management, or sometimes that is also called demand paging, where we just mentioned that I need not put the entire address space of the entire program within the main memory simultaneously, because all the instructions are not going to be executed at a time. You have to execute one instruction at a time. So first you execute the first instruction, then only you go to the second instruction. So when I want to execute the first instruction, it is sufficient if the first instruction is available in the main memory. The second instruction can be brought later on when that is needed. Okay, so even if I have limited amount of main memory, even then a big program can be executed. But of course, your secondary storage or that disk should have sufficient space to store the entire program. Okay, so that we'll do in the next class.